Hello class, welcome to lesson 6.6, conditions of special parallelograms. So the essential question we want to address today is which properties of the diagonals of a parallelogram help you to classify a parallelogram? So we want to be able to identify rhombuses, rectangles, and squares by the characteristics of their diagonals. Okay, so we're going to begin with the properties of what we call a rhombus. We remember that a rhombus in this case is a parallelogram where the sides are congruent. So here we're going to talk about the property of the diagonals. So if the diagonals of a parallelogram are perpendicular bisectors, then that means the parallelogram has to be a rhombus. This was the reverse of the theorem 616 that we talked about in the previous lesson. The other theorem that we discussed was the fact that if you have a diagonal that crosses a rhombus, so in this case, diagonal BD, we know that the diagonals bisect the angles if you have a rhombus. Now, the opposite of that theorem, or the converse of theorem 617, states that if the diagonal bisects the two angles, then the parallelogram has to be a rhombus. Okay, so that's the reverse. So we're going to look at an example in which we prove one of these theorems. So we're going to prove the converse of, in this case, the theorem 616, which was this top theorem. We're going to prove this. So we know that in this case, we have a right angle that BE is perpendicular to AC, the diagonal, and that it's a perpendicular bisector. So that means that in this case, AE is equal to EC in this case. Okay, so given this information, we want to be able to prove that we have a rhombus here. So if we're going to do this, well, we're going to keep in mind that because we have a right angle here, because these are perpendicular, that means that all of these angles have to be right angles. Okay, so that's something that we need to be aware of, that they're all right angles, and because they're all right angles, that means they must be congruent. Now, if we consider these triangles, because we know that AE is, or rather that BE is congruent to ED, then that must mean that if we look at these triangles, we know that we got a side, angle, and side, and similarly we got a side, angle, and side. Well, we know that those triangles must be congruent by SAS. And that's the case with all of these triangles. So all of these triangles have to be congruent by SAS. Now, because of that, we can use CPCTC to show that AB, this side, is the same for this triangle as it is for this side. And that is the same as this side of that triangle, and so on. So we can show that all of these sides are congruent. And therefore, because the parallelogram has 4 congruent sides, we can prove that it is a rhombus. We can conclude. And that is the end of the proof. Okay, so we're going to go ahead and prove the converse of theorem 6, I believe it was 617, or 616 or 617, but the other theorem that we included. And that was that if you have opposite angles, or if you have a diagonal that bisects the angles on the vertex, cuts it in half, then that means you have a parallelogram, or you have a rhombus parallelogram. So we know that if we were to look at this diagonal, we know that this diagonal is congruent to itself because of the reflexive property. We also know that because we know that these angles are congruent, we can show that these two triangles are congruent by angle. In this case, it should really say angle, side, angle. So we know that FGH is congruent by angle, side, angle. So this should say ASA rather than SAS. And that this triangle on the bottom is congruent by ASA. Okay, so those two triangles are congruent. And therefore, it stands to reason that by the CPCTC, because the two triangles are congruent, that means that this side right here has to be congruent to this side right here because they, in this case, they correspond to each other on the triangle. Okay, so now that we know those triangles are true, we know that piece of information. We also know that angle 1 is congruent to angle 4 because they're alternate interior angles. Remember that we know that we want to prove that this is parallel. But we do know that in this case, since this is a parallelogram, we're given that this is a parallelogram, we know that these are parallel. And therefore, if I look at, for example, let's see here, these two angles, or these two lines, or let's extend those into lines here, and we look at this transversal, angle 1 and angle 4 are alternate interior angles. They're on opposite sides of the transversal here. So now that we have that visual, we know that they're alternate interior angles, and therefore they must be congruent. Similarly, for 2 and 3, they're alternate interior angles as well. And therefore, by transitive property, they have to be congruent to each other. And so 1, 2, 3, and 4 are congruent. So now that we know that 1 and 3 are congruent, so we know that these are congruent, then by the converse of the isosceles triangle theorem, remember that the converse of the isosceles triangle theorem states that if you have a triangle, if you have two opposite side or opposite angles that are congruent, like these two on the bottom, then that means that you have an isosceles triangle. That means that you can conclude that these two opposite sides are congruent, and therefore the triangle is isosceles. So now that we know that these angles are congruent, that means that these two sides are congruent, FG and GH. And so we can say that those are congruent there. And similarly for the bottom triangle, these are congruent, and therefore they're all congruent to each other by the transitive property. Since we know that all sides are congruent in this example of a parallelogram, that means we're dealing with a rhombus, and that is the end of the proof. Okay, so let's look at another theorem. This theorem is for the rectangle. So if we want to classify something as a rectangle, remember that theorem 618 stated that if you have a rectangle, the diagonals have to be congruent. So if you reverse that, you can say that if the diagonals of a parallelogram are congruent, then you're dealing with a rectangle. Remember that all of these parts of this diagonal, or the two diagonals, are congruent. Remember also that you know that because it's a rectangle, then that means that these are right angles. So you're concluding that those are right angles in order to make that into a rectangle, in order to conclude that. So let's go ahead and prove this. So looking at this diagram, we know that it's a parallelogram, so we know that these sides are parallel, but what we're trying to prove is that it's a rectangle. So we do know that GJ is congruent to HF, because that's what we're trying to prove. We're trying to prove the converse of the theorem that we just stated earlier. Okay, so using this information, we know it's a parallelogram. So that means we know that the opposite sides are parallel, but they're also congruent by theorem 6.7. So that was in the previous one of the previous lessons. So that means that these have to be congruent and these have to be congruent. So now, because GJ is congruent to HF, because the diagonals are congruent, then that means, so if we look at, for example, just looking at this diagonal, we know that that's congruent to this other diagonal. So those two diagonals are congruent. Now, if you look at these two triangles, that means that these two triangles here, so this triangle, which I'll say number 1, and I'll erase this. So you can see that triangle there right here that I've outlined. And this triangle on the bottom, those two triangles have to be congruent by side, side, side. So we got a side, side, and a side in the middle. And then the side in the middle, side, side. So those two triangles have to be congruent by SSS. Okay, so now that we established that those two triangles are indeed congruent, then we can use the CPCTC. Because those two triangles are congruent, that means that the angles that correspond to the triangles are also congruent. So in this case, we're interested in CF or GFJ rather. So this angle in here has to be congruent to right here. Let's see here, GFJ. So this entire angle has to be congruent to this angle. 8 in this case, that's, or rather, I meant to say HJF. So that's going to be this angle right here, rather. Apologize for that, because we're talking about this triangle. So I'll draw that triangle actually. We got this triangle on the left, and then that overlaps with the triangle on the right. So we're trying to say that these two angles are congruent because they correspond to each other. And indeed, they do look like they do. So by the CPCTC, those have to be congruent. So by theorem 6.8, we know that the consecutive angles, these two angles here, they're consecutive. We know that they're supplementary, so they do add up to 180. And because they're supplementary and they're congruent, that means they must be right angles because they add up to 180 and they're the same measure, so they have to be 90. 90 plus 90 is 180. So therefore, we can conclude that those are indeed right angles. So we're going to conclude those two are right. Now by theorem 6.9, we know that opposite angles are congruent. So the opposite angle to angle F is angle H. So this has to be right. The opposite angle to J is G. So that has to be a right angle. And therefore, we establish that all these angles are right angles. And therefore, the parallelogram is a rectangle. And that is the end of the proof. All right, so now let's look at squares. So squares have properties we mentioned of a rectangle and a rhombus. So we mentioned that a square is a rhombus. A square is a rectangle. A rectangle is not a square. A rhombus is not a square. And let's briefly talk to those properties. So we know that a square specifically has the property where the diagonals are the same length and the diagonals are perpendicular. And that's because the dimensions here are the same, and that forces the diagonals to be perpendicular. So we also know, and that's a rhombus property. This is a property of a rhombus. We also know that the square has the diagonals the same length. And so this is the rectangle property. So this is what makes it a rectangle. So we know that a square is a rhombus because of this property. We also know that a square is a rectangle because of this property. But a rectangle is not a square because a rectangle does not have the rhombus property. And a rhombus does not have the rectangle property. So similarly, a rhombus is not a square. So let's look at an example here. So we want to conclude whether the given parallelogram is a rhombus, rectangle, or square. So if we look at the first one, we have here that we have that this angle is congruent to this angle, which means that this has cut that angle in half. So that's a property of a rhombus. We also know that these two sides are congruent. Okay, so we know that those angles are the same. We know that these sides are the same. So what we're going to do is we're going to get some more information out of this. Since we know that these two angles are the same, these two sides are the same, what we're going to say is that we know that this diagonal is congruent to itself by the reflexive property. And then we know, therefore, that by side angle side and side angle side, that these two triangles are congruent. And therefore, we know that this is congruent to this, but we also know that this is congruent to this. And that's important for a rhombus. So that means that these two angles got cut in half. These two angles got cut in half, and they have to be congruent. So therefore, we can say that for certain that this is a rhombus because the angle got cut in half. Now, for the second one, we know that we have a property that the diagonals are perpendicular, so that follows a rhombus property. we also have that the diagonals are all congruent, which follows a rectangular property. So this is a rectangle. So based off of these two properties, we know that since it's a rhombus and a rectangle, that overall it has to be a square. Because remember, a square is both a rectangle and a rhombus, so we can classify it as such. All right, so for these examples, we have that these two diagonals are congruent here, but we don't have that these are congruent, unfortunately. So that's a big question mark. We cannot there's no way that we can figure out whether they're congruent or not. So there's not enough information here. We cannot conclude that it is necessarily a rectangle, for instance. Actually, there is a way to tell what these, even though we don't know what these are, we can actually, there is a way, now that I think about it, to figure this out. We do know that in the directions that this is a parallelogram, and because it is a parallelogram after all, that would mean that these are parallel, but that also means that the diagonals bisect each other. And that's a property of a parallelogram. That's not a property of necessarily a rhombus, rectangle, or square. It's just a generic property of a parallelogram that applies to all three of these. So therefore, the diagonals do bisect each other. And so if this is bisected, then this has to be the same length. And if this is bisected, this does have to be the same length. So we do actually know this after all, now that I think about it. And so therefore, these are all congruent. And therefore, this is a rectangle in this case. So we can actually show that this is a rectangle by the converse of one of those other theorems. Okay, so now looking at this example, we know that these two angles are congruent, and they're also congruent to this angle. We know that this is a parallelogram, which means that for a parallelogram, the opposite angles are congruent. So U and W are congruent. And so if U and W are congruent and this is congruent to that, well, then that stands to reason that this is also congruent. And therefore, we can deduce that because this diagonal cut this angle in half and this angle in half, therefore, this must be a rhombus. All right, so we want to look for the values of x and y in the given rhombus. So we have here that because it is a rhombus, we know that these are the same length here, these sides. And we also know that these angles have to be the same because for a rhombus, the angle gets cut in half. So we can set these two equal to each other, and then we can also set these two equal to each other. So let's set the circled one equal to each other first. So I'm going to add y to both sides, and I'll get 6y plus 5 on the right-hand side. Then I will subtract 5. So we have 60 equals 6y, divide by 6. So y is equal to 10. 6 times 10 is 60. So we have our value of y. Now let's set these the rectangled ones together. So we got 4x plus 3 equals 5x minus 10. So we can solve this. We're going to subtract 4x on both sides. So we get 3 equals x minus 10. So x has to be 13. 13 minus 10 is 3. All right, guys, that's going to do it for the video. I hope you found this informative and useful and that you learned something from this. And as usual, I'll see you in the next one.